Hello! Last time, we introduced the best response function as a tool for finding a Nash equilibrium. In this lecture, we will discuss the Cournot's oligopoly model as an example of this. Oligopoly means that a small number of firms dominate a certain market. In the general setting, we have a set N of N firms producing a single type of goods sold on the common market. Each firm I needs to decide the number of units of goods Qi to produce. These are the variables. The production cost is a function Ci of Qi, where Ci is a given increasing function. Given a strategy profile Q, a unit of the goods sell for the price of P of Q, where P is a given non-increasing function on the sum of the Qi's. This means that the more goods there are in the market, the lower the price. The utility of firm I in the strategy profile Q is Ui of Q, which is equal to Qi times P of Q minus Ci of Qi. That is, the revenue for selling Qi units minus the production cost. Now this is quite a general problem with many ways that you can define the production cost function and the price function. But two researchers, Zidorowski and Yakovich, proved that a Nash equilibrium always exists under some continuity and differentiability assumptions on P and C. For us, we will discuss the special case where we have linear costs and prices. So suppose we assume that the cost Ci of Qi is C times Qi for all I, meaning the cost is linear, and we have the same unit cost C for all the firms. We also assume that the price P of Q is the max of 0 or alpha minus the sum of the Qj's. This means that the price starts at alpha, decreases by 1 for each unit produced, and the minimum price is 0. We will also assume that 0 is less than C less than alpha. The production cost of 1 unit is less than the starting price. Using the formula for the utility, we see that Ui of Q is Qi times P of Q minus Ci of Q of I, and there are two cases depending on P of Q. If alpha minus the sum of the Qj's is at least 0, then this utility is Qi times alpha minus C minus the sum of the Qj's. Double check that this formula is correct. On the other hand, if alpha minus the sum of Qj's is less than 0, then the price is 0. So the utility is minus C times Qi. Looking at the formula for the utility, when is it possible to make a profit? And the answer is when alpha minus C minus the sum is greater than 0. We now focus on a particular firm I, and we will separate Qi from the sum. So alpha minus C minus Qi minus the sum of Qj's that are not I's is greater than 0. Rearranging this gives us an upper bound on Qi. Now, it does not make sense for Qi if this right-hand side expression is less than or equal to 0. So we will assume that the right-hand side expression is greater than 0. The utility is then Qi times alpha minus C minus Qi minus the sum of Qj's not equal to I. Treating Qi as the variable, this is really a quadratic expression of Qi. So this utility is maximized when Qi is equal to this expression here. We can use calculus or any other methods to find that. So the best response function for firm I given the production of the other firms Q minus I is the expression shown here. We see that there are two cases here. One case is when we can make a profit, And the other case is when we cannot make a profit, in which case we will produce 0. So that is the best response function for a firm I. We now simplify this even further down to just 2 firms. And we suppose that Q star, which is Q1 star, Q2 star, is a Nash equilibrium. By our lemma from last time, a player's choice must be the best response to the other player's choice. So Q1 star is in the best response function for player 1 and vice versa. Now you should verify that we can assume that Q1 star and Q2 star are both greater than 0. Then we have these two equations. Q1 star is equal to alpha minus C minus Q2 star divided by 2, and Q2 star is equal to alpha minus C minus Q1 star divided by 2. Solving these two equations gives us the value of Q1 star and Q2 star are both alpha minus C divided by 3. So this is the amount we expect each firm to produce at equilibrium. So then the price at equilibrium is alpha minus Q1 star minus Q2 star, and that is equal to alpha over 3 plus 2C over 3. And the profit for each firm at equilibrium is the utility, which is going to be alpha minus C squared divided by 9. So this is what we expect to happen when there are just 2 firms. Now these numbers might not make that much sense here, but we can derive 2 interesting notes from these numbers. First, suppose the 2 firms can collude, and together they produce Q units in total. The total profit is then Q times alpha minus C minus Q, which is maximized at Q equals to alpha minus C over 2. We can calculate the total profit, which is then alpha minus C squared divided by 4. Splitting the profit equally among the 2 firms, we get that each firm gets alpha minus C squared over 8, which is greater than alpha minus C squared over 9, the profit we expect at equilibrium. And you can check that the price does go up if the 2 firms collude. So in a small sense, this tells us that colluding is beneficial for the companies, but bad for the consumers. Now in the general case with n firms, if Q star is a Nash equilibrium, then Qi star is this formula here. And this gives us a system of linear equations, which gives us Qi star is equal to alpha minus C over n plus 1. And we can calculate that the price here is 1 over n plus 1 times alpha plus n over n plus 1 times C. We see that as n goes to infinity, the price goes to C. Meaning, as more firms are involved in the market, the expected market price is going to get closer to the production cost. So that is an example of using the best response function to find a Nash equilibrium. In the next lecture, we will use dominating or dominated strategies to find one.